Welcome to the Stutzman channel, and this is part 2 of how to check capacitors on an AC unit or heat pump while the unit is running. And in this video we're going to be explaining where this magic number 2652.58, where does it come from? Okay, so to get started and to make it a little bit more interesting, I got a little quiz here for you guys. I've got 3 diagrams down here on the bottom, as you can see. So this here first one here, we have a 120 volt source. It's at 60 hertz. I have a 100 microfarad capacitor, and I have a 120 volt 15 watt light bulb. Now what I want to know is the light bulb going to be, is it going to be bright, dim, or is it going to be no light? This is going to be A. Now for B, I have exactly the same source. I have a 120 volt source, 60 hertz, 120 volt bulb, 15 watts, but now I have a 1 microfarad capacitor. And I also want to know, is it going to be bright, dim, or is it going to be no light? And finally, in part C, I have a 120 volt DC source, I have a 100 microfarad capacitor, still the bulb is the same as 120 volt 15 watt. And again, is the light going to be bright, dim, or no light? So before you answer that questions, these are 3 examples, and you can put them down in the comments, you know, so A is going to be this, B will be that, and C will be this. Before you answer, we're going to go through of how this here 2652.58, how is it derived, where does it come from, and why do we take this number and we take it and we multiply it times the amps, and then our result we get, we divide it by the voltage. So let's get started. So the first thing, where does it come from? First we're going to have to look at an equation, but I promise this math is very simple. It's only multiplying and dividing. This is all 3rd, 4th grade math. Alright, so we're going to start off with the equation here. It's going to be x sub c equals 1 over 2 pi times the frequency times the capacitance. Now, x is reactance. Now, and c is capacitance. Now, as I'm explaining this equation, and as you're looking at it, be thinking about these 3 circuits down here, and you should be able to answer it. Now, reactance it's the opposition. The capacitor is offering opposition to the current, which is measured in ohms. It's basically resistance. You can think of it like AC resistance. But now look at it. This is an inverse proportional equation, meaning if we look, there's only 2 things here. Frequency, which is measured in hertz. C is capacitance, which is measured in farads. Now, if the frequency, let's say, was to go up, what is going to happen to the inductive reactance? It is going to go down. This is where the inverse comes in. So frequency goes up, inductive reactance goes up. I mean, the capacitive reactance goes up. So if the capacitive reactance goes up, which is measured in ohms, just like resistance for DC resistance, it is going to go down. Resistance goes down, then what's going to happen? The current is going to go up, just like a DC circuit. Now, if the capacitance goes up, well, it's the same exact thing. Then our capacitive reactance is going to go down. And obviously, if you have the frequency or the capacitance was to go down, then our capacitive reactance is going to go up. So it's just backwards, okay? Just backwards. Now, you could be thinking about this down here. Now this equation right here only works on sinusoidal AC sources. So it's one that's going to be generating a sine wave, okay? All right. So now that we got that out of the way, let's see how we can take this equation and we start manipulating it. All right. What we want is capacitance. All right. We don't want inductive capacitance. At least we don't want to have it equal right now to this. We want to have capacitance equals to this in terms of capacitive reactance. So let's transpose the equation. So let's see if I multiply both sides. Now I already know what it's going to be, but this is so you can see how equation is transposed. All right. I want C equal to something, right? So let's multiply both sides of the equation by 2 pi Fc. 2 times pi times frequency times capacitance. So if I multiply this side of the equation, and then I do the same exact thing over here, I have not changed that equation. It's still exactly the same thing. Now my 2 pi Fc will cancel out, leaving me with 1 on the right hand side. So let's just bring him down. Now I'm going to go over here and I'm going to put down 2 pi Fc, and of course we're multiplying that times X sub C, our capacitive reactance. Okay? Now I want to solve for C. So what do? We're going to take and we're going to divide both sides of the equation by 2 pi f x sub c. I do the same thing over here. Okay? So far so good. Now my x sub c will cancel out. My 2 pi will cancel out. My frequency will cancel out, leaving me with only C for capacitance, which is equal to 1 over 2 pi f x sub c. Okay, that wasn't bad now, was it? All right. So I'm going to rewrite the equation up here at the top. And that's what we're going to start with, because that's what we're looking for. Remember, we're trying to find a capacitance. That's what we did when we was out there at the AC unit. Okay? So let's rewrite this equation right up here. C equals 1 divided by 2 pi f x sub c. Okay. Now, 1 is a constant, it's a number. 2 is a number. Pi is a number. It's an irrational number, just goes on forever. Approximately 3.14. We know what F is. F is our frequency. This is the line frequency. And in North America, that is 60 hertz. And by the way, I'm going to talk to you about another number. 2652.58, a magic number, works here in North America where you have a line frequency of 60 hertz. If you were in another country, such as over in Europe, a country over there, then that's going to be 50 hertz. So you're going to have another number. So we'll do that number also. Now, if I take, and what we want to do is we want to focus on this part right here for right now. So if I take and I say 1 divided by 2 pi, my frequency is 60. If I multiply that out, guess what I get? I am going to get 0.0026528. There's what you're going to get, but it goes on and on and on, but we're going to round it off, okay, just like what we have over here, 2652.58. You see, we got the same number. Now this number is going to give us the capacitance in farads, but we want the answer to come out into microfarads, because that's what's out there on the unit. microfarads. So how do we do that? We're going to shift the decimal point 6 places over to the right. 10 to the minus 6, that'll be for micro. So when I shift it over, that is going to give me 20. So if I go 1, 2, 3, 4, 5, 6, I will get 2652.58. And now you can see that that number and that number, there's our magic number. Okay, now let's explain why we multiply times the amps with this number, and then we take the result and then we divide it by the voltage that's across the capacitor. Okay? All right, we're going to need one more equation. Because, look, X sub C, capacitive reactance. We got to put something in this equation to make this thing work. So we're going to rely on Ohm's law. All right, so we start in Ohm's law. Of course, you know, is voltage is equal to current times resistance. You remember I said a capacitive reactance was just like resistance? Okay. And do you remember that we took our current, we measured the amount of current that was for the capacitor? I should say, you know, the current is not going through the capacitor, because what we're measuring is charge and discharge current. And that's another video. I don't want to get sidetracked into that, how a capacitor works. But we're looking at the current there, and we checked across the capacitor to see what the voltage is. So let's just change this a little bit. So that voltage that we measured across the capacitor, let's just call it voltage across the capacitor. So we're going to say V sub C equals, and then here for the current, we're going to say the current I sub C, the current for the capacitor. Now, this here resistance, as you already know, which I just mentioned earlier, that is our capacitive reactance. So that is going to be X sub C. Now, we want, remember, we want this over here for this. So all we have to do is transpose the equation. So now, capacitive reactance is going to be equal to the voltage across the capacitor divided by the current for the capacitor. There is our equation, okay? Now, I need a little more room, so let me get rid of this part, okay? And I'm just going to move this equation right up here at the top. So I'm going to say capacitive reactance is equal to the voltage across the capacitor divided by the current for the capacitor. All right. Now to give me a little bit of room in there now. Still with me? Everything still good? Okay. Just kind of still thinking about the 3 circuits down there, right? All right. All right, so here's where we got... when we got this number 1 divided by 2 pi f, we had 2652.58, right? So I could say 2652.58, right? And I could, when I divide that out, I could do it just like this, right? And then I could put my X sub C down there, my capacitive reactance. That to what I just did earlier is the same exact thing. Okay, so now this X sub C. All right, so still, let's take a look at, so you can see what I'm going to do next. If I took a number, say like 3 divided by 1, 6, all right? You see it wrote out like that. Now, you write down your first number, right? Then you say times, then you invert the second number, you get 1, 6, and then you get, you invert that number, and you get 6 over 1, and that's going to be 18 over 1, which is equal to 18. Simple math, right? Now I can do the same thing. When I get a number like this and I'm dividing fractions, this is the way I do it. I say, let me find some room here. I'll say 3 divided by 1, right? Then I do this, and then I do 1 divided by 6, okay? Now you can see that's 18, so I'm going to just erase this little part right in here. And what I do is I take and I multiply the outside numbers, okay? 3 times 6 is 18. Put it on top, draw your line. 1 times 1 is 1. Put it on the bottom. 18, right? Okay? Now, we're going to take that same thought, we're going to do the same exact thing with this here equation over here, or this here little expression. All right. 2652.58, I'm going to write it right here. Now that's the same thing, I could do that, right, and put a 1 underneath. Then I could draw my line underneath, which is this one right here. Now I have my x sub c. Look, there it is, right there. Now I'm going to put bc divided by I sub c, okay? Now you multiply the outside numbers, what do we get? We get 2652.58, right? Times current current for the capacitor divided by 1 times VC is VC. And that's exactly what we did in the first video. We took that 2652.58, we multiplied it times the current that's for the capacitor, and then we took that result and then we divided it by the capacitor, the voltage across the capacitor. All right, so now you see all how that's done. Y'all got it figured out yet? Okay. Now, let's talk a little bit. I promised to talk a little bit about trying to make myself some room here. Now, I talked a little bit about this here bleeder resistor. If you take a screwdriver in there, and let's say this capacitor is charged up. Most of the time, if everything's working good and you don't have any open windings in your motor, you know, you're not going to find anything in there because it's going to be discharged. However, what if you did? What if they had a problem and this capacitor was charged up? How much current is going to flow when you taking a screwdriver and just bridge, you know, the two terminals, say for the Herm to the common or the fan to the common, all right? So, there's an equation for that. So we have the current through the capacitor, right? That is going to be equal to the capacitance, measured in farads. Remember mine was 40 microfarads. And that is going to be multiplied times the derivative of the voltage with respect to the derivative of time. Now that sounds pretty complicated. This is actually a little bit of calculus here, but simple. It's just the rate of change. How fast is this voltage going to be changing with respect to time? Now, let's use an example. Let's say the capacitor was charged up to 300 volts. Yeah, that's a pretty good figure right there. So let's say we have our capacitor. Now we had what do we have? We had a 40 microfarad, right? So that is going to be 40 times 10 to the minus 6 farads, right? Now we set our voltage, a rate of change of voltage. Let's say it's charged at 300 volts. Now I bridge across it. How much time do you think that'd be? Let's give it some, let's say 1 millisecond. That's how much time it takes for it, say, to discharge. And we're going from 300 volts down to 0 volts. And we're doing that in 1 milliseconds. So we have a change of voltage of, let's say 300 volts, because we went from 300 volts down to 0 volts. And now we did that in 1 millisecond. And we're going to have that as 0.001, right? So what is that? That is going to be 300,000. So we have 300,000, right? 300 divided by 0.001, okay? And then we take this and we're going to multiply that times 40 times 10 to the minus 6. So let's see if we can kind of simplify this a little bit. So let's see, 40 times 10 to the minus 6. And 300,000 is the same thing as 300 times 10 to the third. So then 40 times 300, that's 1,200. So that's 4, let's see, 4 times 3 is 12. We got 1, 2, 3. So we got 1, 2, 3 times 10. That's going to be 2 to the minus 3, right? And then if we take that and we move it back 3 places, that's going to be equal to 12 amps. So we're going to have 12 amps of current flowing, you know, not through the capacitor, but there's going to be 12 amps of current that's going to be discharged. So basically when you got this current, you're going to have heat, and you ain't got nothing inside this thing but aluminum foil. So it's not a good idea if you got a capacitor charged up this much. And you can see the more farads you have, the more the current's going to be. And the faster that voltage change, the more higher the voltage is and the faster it changes, then you're also going to have more current. Okay, so let's go to the bleeder resistor a little bit. And we'll talk about that a little bit. And this way, this is kind of coinciding, so we don't jump this thing off with a screwdriver or something. Because 12 amps, you know, for the capacitor there, that's quite a bit of heat there, right? It's a very quick amount of time, but why put the capacitor under stress? Okay, now on this here bleeder resistor, and I showed this in the first video, you can just see it a little bit here. It's just a test light. And this here test light, I took the spring, I took the bulb out, and then I just took a 20,000 ohm 5-watt resistor. I soldered it to one end here. That will go to this here, that will go to this probe here. And then over on the other end of the resistor, then it goes to this here lead. And then I just put a smaller clip on here so it wouldn't be, you know, so hard to try to get in there on the terminals. And then of course, just a piece of shrink tubing. So we got a 20,000 ohm 5-watt resistor. So let's take a look at that. All right, if I take the capacitor, and then when I take and it's charged up, and then there's this here resistor, okay? And let's say there's 300 volts. That's on the capacitor. And over here we have our 20K ohm resistor. Well, what we have done there is that we have allowed this current to discharge slowly. And let's look at the specs on it. What's going to happen? This right here is a time constant that's been set up. Time constant is going to be equal to the resistance times the capacitance. Now, if you saw one of my earlier videos, I did one on inductive reactance, where the time constant is equal to L divided by R. Okay? In this case, it's going to be R times C. What that's basically saying, whether you're charging the capacitor through a resistance or you're discharging it, it's going to take a certain amount of time. And it's going to follow an exponential curve. All right. So on this, our resistance is 20 times 10 to the third power. Our capacitance, in my case, was 40 microfarads. So that's 40 times 10 to the minus 6 farads. And if we multiply this out, then we can see that 2 times 4 is 8. So this is going to be 800 times 10 to the minus 3 seconds, or 0.8 seconds. That is one time constant. What that's saying is that it is going to take 0.8 seconds for it to discharge from 300 volts down 37% of the initial value of 300 volts. So it's going to discharge 67%. Okay. Now, what is considered when it is fully discharged is 5 time constants. Now, if you notice, I was out there, I was counting it. So if we're going to do 5 time constants, and this is when you're saying this, the capacitor is fully discharged. Now, also it could be fully charged, but in this case, we're looking at discharge. Then we can say that 5 times our time constant of 0.8 seconds is going to be equal to 4 seconds. So that's why I was out there counting. I was saying 1001, 1002, and I went up to, 5 seconds. So more than enough time, right? Now you can see that the more capacitors you have, the longer it's going to take. Your time constant is going to be more. And of course, the amount of time that it's going to take to discharge it, it's going to take a little more time. But 5 seconds is a pretty good roundabout figure. Okay, with this here bleeder resistor, and we have, how much current is flowing on this thing? Well, let's use a little bit of Ohm's law and see if we can figure it out. So we got voltage is equal to current times resistance. There's our favorite Ohm's law equation. So now let's see, we want current, so current equals the voltage divided by resistance. And that's going to be, we say we're using 300 volts. Our resistance is 20,000 ohms. So 20,000 ohms, we divide that out. Let's say 2 to 3. So, okay, that's going to be, that is going to be 15 milliamps. Now that is quite a big difference from 12 amps that we had earlier, right, that we figured out. Okay, now let's look at the wattage. Let's look at the wattage on the resistor. Make sure we got that right. All right, so we got a 15 milliamps flowing. So now let's use Watt's law. Watt's law is power equals voltage times current. Oh, well, let's use this one here. Let's use the Watt's law using current squared. So if we say power is equal to I squared times R, so power equals, there's our current, so this is 0.15 squared at 20,000 for our resistance. And we multiplied that out, and I believe we're going to get, say 4, 5, that's 225. And I think we're going to get 4.5 watts. So we came in at, we're using a 5-watt resistor. Now keep in mind, this is not a continuous amount of wattage. It's just a pulse, and then the voltage is coming on down. So this is just for a very, very instant, and we're still good. So we're okay. So now let's help the friends out that's around the world that's using 50 hertz. So it's exactly the same thing of what we did to get our magic number. Remember our magic number was 2652.58. Now if that decimal part out there hanging off is a little bothering you a little bit, go ahead and round this number off and you can say it's 2653. Because you can see we just rounded up, right? So you can use that number and you should still be pretty accurate, okay? Getting back to our friends across the world there that has 50 hertz, if we take this here, 1 over, right, 2 pi f, right, and we've said this would be x of c because we're looking for capacitance. So we got 1, 2 pi times 50. Now if you divide that out, you should get 3183.09. But in this case, just like on the 0.58, drop to 0.09, right? And just say 3183 is going to be your magic number if you're using 50 hertz, right? And if you've got 60 hertz, you're going to be using this number, 2653. All right, I think that's about it. I think I covered everything that I was going to cover. So did you guys kind of come up with the answers there? So anyway, put your answers down in the comments and so I can see what you come up with. Just remember, the secret to understanding this is what I said earlier about this here equation. This is an inverse proportional equation up here, right? This one right here, okay? So you can see that as frequency goes up, and here's the other one right over here. Let me do the one for that capacitor reactance. Of course, it's the same thing except we're just transposing the capacitance. So there you go. So your capacitor reactance, you see, as the frequency or the capacitance goes up, then this here is going to go down. And if one or the other comes down, then that'll go up. So anyway, that's going to wrap this video up. Hope it helps you out. Now you understand how we got this here number and why we multiplied times the amps and we divided by the volts. We'll see you guys in the next one, and you take care.